Okay, so last section we're going to take a look at is 5.5. And 5.5 is still on logarithms, but we're going to look at a few different things now. We didn't really spend any time graphing, so we're going to talk about how you graph a log function and how you do it on the calculator and how you can do it on paper. Okay, so we'll look at both. We'll also look at transformations, okay? Shifting up and down, left and right. But the nice thing is, all the transformations are exactly the same as everything we've studied all year. There's no difference. All right, so sometimes we might want to deal with a logarithm that doesn't have a base 10 or a base e. So I want to show you how we can type in base 10 or base e, basically on any calculator. It doesn't even have to be a graphing one. So let's start with something like this. Let's say we had y equals log base a on x. And you wanted to actually figure out what y is. Okay, let's say a and x were numbers. Well, if a is a 10, you're fine, because you have a button for that. And if a was the number e, you're okay, because you have a button for that, ln. But those are the only two you have buttons for. If you had a problem like this, I haven't shown you how to type that in. Now, some calculators have a way to type it in, some don't. I know some people are using an older calculator, and there is no way to type in a log with a different base directly on that calculator. So I'm going to show you a way that works on every calculator. All right, so let's take a look at that equation. What I would like to do is somehow rewrite it. And I still want to have y by itself, but I'd like to have something different over here, something that I can actually type in. So let's start by taking this equation and changing it to exponential form. What's my base in that equation? Yep. A is my base. Logarithm always equals what kind of number? Yep. Exponent. And what ends up by itself on the other side? Yep. X. Very good. All right. So all I did was change to exponential form. Now, I'd like to get the y out from being an exponent, but I can only move the y if I have what on each side? When are we allowed to take an exponent and move it to what's in front? Yep.
A log on both sides?
Right, we can take a log of both sides. So let's do that next. So you're like, well, wait, are we just changing it back to log form? Well, it's going to be log form again, but it's going to look a little different on the right. And it's going to look like something you can put in on a calculator. So let's take the log on both sides. Now, when I took the log of both sides, what base am I assuming here? 10. That's good. We have a button for base 10. We don't have a button for base A, but we do for base 10. Okay. Now, what can I do with the y? Yeah?
Did you put the y in front?
Yeah, now we put the y in front. So to get from this step to this step, take log of both sides. Now move the y in front. So we have y times something equals something. And how would you get the y by itself now?
by each side by log n.
Right. Divide each side by log n. So after all that work, we've ended up exactly with the same thing on the left-hand side that we started with. Y is back by itself. But the right-hand side looks a little different. It's log x over log a. So let's look at both of these. So let's call this box 1. Box 1 is equal to y. Let's call this box 2. Box 2 is equal to y. So what does that mean about box 1 and box 2? Yeah?
That they're equal.
Yeah. Box 1 equals box 2. Box 1 equals box 2. And this is the change of base formula. The idea here is to see the pattern, so you don't have to go through those steps every time. So box 1 is log base a of x equals log x over log a. That's the change of base formula. So let me put some numbers in and see if you could tell me how to do it. Let's say I wanted to know log base 3 of 12. How do you think I would rewrite that so I can type it in on my calculator? Yeah?
Log 12 divided by log of 3.
Yes. You take the log of 12 and you divide by the log of 3. So the pattern is, if you have to take a log of something that has a base other than a 10 or an e, you take the log of the argument, you put that in the top, and you divide by the log of the base, and you put that in the bottom. Now, it ends up that you could also do this. Whether you use the log or you use ln, it doesn't make a difference. You could do either one. Don't mix them. Let me show you. So let's take log 12 divided by log 3. You get 2.26. Keeps going. ln 12 divided by ln 3. 2.26. Comes out exactly the same. And that's called the change of base formula. I generally do it this way, with just the log button. So I'm using a base 10. But if you wanted, you could use the ln button, but you can't mix them. Either use log in the top and the bottom, or use ln in the top and the bottom. So just a shortcut for having to go through all that work every time. Changing it to exponential form, taking the log of each side, and then moving the exponent in the front. This is what would happen every time. So we'll use this formula from now on. All right, so they want us to graph log base 3 of x, but base 3 isn't a log that we have a button for. So before we can type this in, we have to rewrite it. How can I rewrite log base 3 of x so I can put it into y1? And I'll give you a hint. It's always going to be rewritten as a fraction. Oh, Quinn, could you tell me how to rewrite it?
Log x divided by log 3.
Good. Log x divided by log 3. All right, let's type that in and then see what it looks like. Now remember, log functions, the calculator doesn't do a good job of them. You should have a vertical asymptote, but the calculator can't draw that part of the log because it's too steep. So keep that in mind. So log x divided by log 3. start with zoom 6. Right. Let's put that over here. And remember, what that should really look like is it should keep dropping down. In fact, I can kind of show you. It almost looks like it stops at -2 going down. Does anybody disagree with that, the way it looks right there? Looks like it stops pretty close to -2. Well, zoom in on -2 and watch what happens. Here's -2 right there. Does it look like it's still stopping at -2? No, now it looks like it's going past it. Now we're at -1, -2, now we're down to -3. It didn't look like it went down to -3 at all. So if you zoom in, you can get a better picture. But then you can't see the big picture, right? And actually, I think I dragged it over before it finished graphing. Sorry about that. All right, so make sure you understand that this goes down like that. And what do we have right there that's stopping it from going further to the left? What do we call that? Yep. Yep, we have a vertical asymptote there. The vertical asymptote for a log function, if you don't transform it, is always the y-axis. All right, so now let's see if we can answer some questions. Okay, they want to know the domain and the range. All right, we got a good picture. That's good. So we got a good picture. What's the domain? Think about how far left we go and how far right we're going to go. Yep.
0 not including into infinity.
Yep. The domain of every single log function without a transformation is 0 to infinity. If you shift that left or right, you can change that. How about the range? How high and low does it look like the log function goes? Oh, Jamie? Yep, it does go down forever and it goes up forever. You can see it goes down forever because it drops off very, very sharp. But it does go up forever. It's just extremely slow. Very, very slow. Could you ever change the range of a log function? No. I don't care if you shift it up or down, or you stretch it up or down, or you compress it. It goes up and down forever. So you can't change the range. So that is always the range for every log. Right. That's all they want. So there's our complete graph. Questions on that? Okay. Let's look at this. So transformations. There are generally 6 transformations that could happen. 2 shifts, 2 stretches, 2 reflections. Each one of them is indicated by the letters A, B, C, and D. Let's label them. And does anybody remember what A does? That's adding, or it could be subtracting, but it's inside the parentheses. It's inside the function. Compared to D, which is adding and subtracting outside. Okay?
Horizontal shift.
Yep. That's a horizontal shift. Jess, which way would plus move? Which way would plus move?
Plus would move it. Sorry, to the left.
To the left. So plus would move it to the left. And Chris, which way would minus move it? To the right. Okay. So there's A. How about B? B is still inside the log function, But now it's multiplication. It's not addition or subtraction.
Horizontal stretch.
So there's your horizontal stretch. Remember, like the shift, it is backwards. The bigger you make B, the more compressed it gets. The smaller you make B, the more stretched it gets. So for example, if B was 8, that would actually be a compression by 8. It would squish it 8 times as much. If B was 1/4, that would stretch it 4 times as much. So A and B are always opposites. Okay. What about C? Now we are outside of the log function. And C is multiplication. Yep.
Vertical stretch.
That's a vertical stretch. Okay, nothing backwards about that. Bigger number stretches it bigger. A fraction would make it smaller, like a fraction less than 1. And what about D? What's D, right?
Vertical stretch.
That's your vertical shift. Positive is up, negative is down. Now I said there were 2 other things. You could have a reflection. What's one of the letters that could cause a reflection? Yeah? C could cause a reflection. And how would you know if C is causing a reflection? What kind of number would it have to be? Yeah? It would be a negative. And it would be a vertical reflection. So vertical reflection looks like this. That's vertical. Or you could say we flip it over the x-axis. If B is negative, you'd have a horizontal reflection. That's a horizontal reflection. Okay, so nothing new with all those transformations. All right, so they want us to figure out how you could graph log base 3 of negative x. The base doesn't really matter. The base is just, it has to be the same on the original and the one that you're transforming. If the bases are different, then you're not even comparing the same things. So we're looking at log base 3 of negative x compared to log base 3 of x. All right, so first of all, to get from this to that, how many transformations do you have? Yep, just one. You could have up to 6, but in this one, there's only 1. So to graph, what is it? Y equals log base 3 of negative x. What would you have to do? Yeah.
It's a what's the word? Reflection over the y-axis.
So you would reflect the original, you said, over the y-axis?
Yeah.
Yep. There you go. So to graph y equals log base 3 of negative x, reflect the original over the y-axis. So we just graphed log base 3 of x on the calculator. Let's just use that to kind of help us. That's fine. I'll just put it like that. So it's going to be mirror imaged over the y-axis. So it's going to look something like that. So what would be the domain now? The domain of the black one, not the I know the blue one is 0 to infinity. I'm flipping that. Yeah. Negative infinity to 0. Here's my domain. What about my range? Shouldn't think about this one at all. Yeah.
negative infinity to infinity.
It's always negative infinity to infinity. I don't care what you do. Do they want anything else? Yep. And they want the vertical asymptote. We haven't done this in a little while, but when you write the equation of a vertical line, what letter does it start with? So, Eileen, do you remember? Equation of a vertical line. Well, think about what kind of lines we can draw on the calculator. And this is one we can't. Think about what the calculator looks like when you go to the screen where you're going to graph. And this would be impossible to do because the screen doesn't look like that. Not sure? Help her out, Declan? Vertical line starts out with what letter? X equals. You cannot do x equals on the calculator. You can only do y equals. You get horizontals. So vertical is x equals. And I can see where it is. It's right here. So what happened to the vertical asymptote when I reflected it? It stayed the same. It doesn't always stay the same, but in this case it stayed the same because your line of reflection was the asymptote. Anytime you reflect something and it's on the line of reflection, it doesn't move. It stays perfectly still. So there's the domain, the range, and the asymptote. Yes?
I don't know how, I don't think I programmed it specifically for this, but on my calculator, when I go to plot, where it has, the y equals thing, I can go to the upper left corner, and I have, an option to do x equals, and I can plot x equals stuff.
Might be something that's built in, because I don't think I have that. You said it's in the upper right corner?
Upper left.
Upper left? Like where? Like what would I press?
Well, it's not there.
Oh, it's just not there.
Yeah.
Okay, so it's not a button on the...
No, it's
It's actually on the screen.
Yeah, it's on the screen in the upper left.
Huh. Yeah, it might just be something like an app that was installed on it or something. I don't know, if you press apps, do you have more than just that one?
Yeah.
Okay, so it's probably something extra. Yeah. Any questions on them? Let's try this one. How can we get log 3 minus x from the original? Well, look at what I wrote here and compare that to this format here. It's not set up the same way. So the first thing we should do is fix that so it looks more like that. And then the A and the B will line up in the right spots. How can I rewrite log of 3 minus x so it looks more like what we're used to seeing? Yep.
Log of negative x plus 3.
Yep. Log of negative x plus 3. Now the A and the B are in the right spot. Okay. So how many transformations do we have here? Yep.
Two transformations?
2. The negative is going to do something, and then the 3 is also going to do something. What does the plus 3 do? Remember, that's addition inside. Yep.
We're still left by 3.
Yep. So shift left 3. And then what about the negative in front of the x? It's just like the last one. So, Kelly? So a reflection over the x-axis would be a vertical flip. That would be if you had a negative like that. Yeah, that's a reflection over the y-axis. reflect over y-axis. Any question on that? They didn't ask us to find the domain or range or anything like that. All right, so graphing. Well, how do we graph? Well, the only thing you really have to find is the vertical asymptote. If you can find where it crosses an axis, that okay, great, that's extra. But the most important thing is the vertical asymptote, because a log function always stays right next to that vertical asymptote, and then it curves away from it. So if this was a vertical asymptote, the log function can basically do one of two things. It's either going to curve away to the right, or it's going to curve away to the left. Or if you flip it, then it could still curve away either left or right, but the curve would be flipped. But the point is, it's going to stay right up next to that curve most of the time, and then bend away from it. So how do we find the vertical asymptote? What number is it at normally if we don't do anything to the graph? What?
0.
Yeah, it's at 0. So if you want to figure out where your vertical asymptote moves to, all you have to do is set the argument equal to 0 and solve it. Remember, this is the argument right here. So the only thing that can affect the vertical asymptote is shifting left and right or stretching left and right. Moving up and down wouldn't do anything to a vertical asymptote. That's why we don't care about the C or the D. So set the argument equal to 0 and solve. And that's it. That's all you really have to do to graph it. I would use the calculator to plot maybe a couple more points. And remember, log functions are only going to curve one way. So if you used your calculator and tried to pick negative values in this case, let's say this was your x-axis, y-axis. Well, if you try to pick negatives on the x-axis, you're going to get an error because the graph doesn't go negative. It only goes positive. So when we plot points, we've got to pick points that would be on the correct side of the asymptote. I can't tell you what side the correct side will always be because it could be flipped. So, but it's only one side. I can tell you that. Right? It shouldn't even say if you need more points, you do. You need more points. I would say 3. Get your asymptote, get 3 points. That's enough. But make sure they are points on the correct side. Whatever side would give you positive numbers. All right, so we'll try an example of maybe one sketch, and then we'll finish up with one word color. So let's see if we can graph. First thing I want to ask is kind of a general question. Are the 3 and the 5 going to have an effect on the vertical asymptote, or no? Yeah.
Yes.
Oh, yeah. They're inside. Anything that's inside the parentheses, that will affect the asymptote. In fact, in this problem, there's nothing outside. It's all inside. Okay, so they want us to find the domain, the range, and the asymptotes. Well, we're going to do the asymptote anyway. So let's take care of that first. What do we set the argument equal to find the new vertical asymptote? It's not going to be 0 anymore. It's going to be shifted and stretched. Well, actually, it's going to be shifted and then compressed. Yeah.
Would it be what you need to get 0 out of what's there?
So,
it'd be like
what do you want to
-5
set?
divided by 3. -5 divided by 3.
Yeah, exactly. So you want to set that equal to 0. And then solve it, which is -5/3. Yep. So what's going to happen here is the asymptote is going to shift 5 units to the left, but then it's going to be compressed back in by a factor of 3. So the asymptote moves out 5, and then that distance it moved out is divided by 3. It's compressed back in. So x equals -5/3. Which, as a decimal, I kind of need to know that if I'm graphing it. What's -5/3? Roughly, yeah?
1.66.
Yeah, -1.6 repeating. So about a little more than -1.5. Okay, so when we draw our graph, we'll put a line a little bit past -1.5. Alright, so let's put that. And we're going to go, it doesn't have to be perfect, it's about -1.6 repeating. So now the graph is either going to curve to the right or it's going to curve to the left. One of those two. To make it easier to get the points, or actually I'll say to make it faster, I'm going to plug this in on the calculator and just use the table. So it's log 3x plus 5 divided by log 2. Log 2. Now, which way do log functions normally curve? To the right or to the left? Think of the basic log function. Which way does it normally go? Yeah?
Right.
To the right. And there's nothing here that's flipping it. There's a shift and a stretch. That doesn't flip it. It is still going to go to the right. If you try to pick points that are to the left, try picking like -3. Watch what happens. Negative. Hopefully my negative button works. Negative. Oh. I've never had a button not work. Okay, well, I can do this. I want to try -3. So let's do 0 minus. I can't do 0. Oh.
From the looks of it kind of looks like the settings reset. Like how you have to.
Alright, so if we try -3, it says error because it doesn't curve that way. So let's pick, I would say, 3 points that are to the right. Let's do 0. Let's do like 5 and 10. That should be fine. Okay, so 0, 2.3. 5, 4.3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 4.3. Good enough. And 10 just above 5. So 1, 2, 3, 4, 5. All right. So I've got my curve, and I know that it's going to get very close to that asymptote and stay right next to it. So we're looking at something that probably looks about like that. If you want a couple more points, you could do more. I don't really think you need any more. Well, that's it. That's all you have to do to make a sketch. So just find that vertical asymptote, get a couple points, and then Just draw your curve. Okay, let's write down the domain. What is the domain in this case? Yeah?
-5/3, not including into infinity.
Yep, it's everything from the asymptote to infinity. 5/3 to infinity. And lastly, what's my range? Well, Lucas?
All negative infinity to
Yep, were you going to say all real numbers? Yeah, that's fine too. All real numbers. Negative infinity to infinity. Okay. Any question before we finish up with a word problem? Okay, so the word problem is going to be having to do with an earthquake. And does anybody know what the name of the scale is that they use to measure earthquakes? Like sometimes they say it's like magnitude 6 or something. That's a scale. Yeah.
Isn't it the Richter scale?
The Richter scale. Yep. So the Richter scale measures the intensity of an earthquake. And the Richter scale has a formula. It's R equals log A over T plus B. So the Richter scale depends on 3 factors to find the intensity of the earthquake. Well, the R is the number that you hear about. Magnitude 4, magnitude 6.5. Okay, that's the number you hear about. A is the amplitude of the vertical ground motion in micrometers. I don't know how they measure that. They must have some tool or instrument that measures it. I know they use seismographs. You can measure earthquakes. I don't know if that's the tool, but A measures some type of movement. T is the period of the wave in the earthquake. If you're not sure what a period of a wave is, that's okay. You don't really need to know a lot about that. But if you think about, like, if you took a huge rock, if you're in a helicopter and you just drop it in like a lake that was, perfectly calm, you'd get a wave. Well, that's basically what an earthquake looks like. There's an energy source causes something to happen, and then there's a wave of energy that comes out from it. Some waves are shorter, like that. Some waves are longer. How long or short the wave is, that's called the period of the wave. All right, so that's measured in time. That's seconds. So it's basically like sometimes you might see this at like a science museum, but they have like a tank and you can create waves in it. And if you stood there and you counted how long it took for, like, say the peak of a wave to pass you and then another peak to pass you, that's the period of the wave. And B is a factor that accounts for the weakening of the wave, because as the wave dissipates from the epicenter, it gets weaker. That's why if you're right near the center of an earthquake, it's more powerful. If you're 600 or 700 miles away, you might not even know it happened. And how it weakens, I don't exactly know. It probably depends on the ground. How is the ground hard and soft? Is it, are you in the mountains? Are you in the desert? Different kind of ground. So basically, they just give you those values. You just plug them into the formula and you calculate the intensity. Does everybody have what the letters stand for and the formula? Next, let's do our last example. So 5 find the intensity of the earthquake. So let's say the values are, A is 300, T is 2.5, and B is 4.3. So find the intensity of the earth. All right. Can someone remind me what's the formula again? R equals
equals log A divided by T plus B.
A divided by T plus B. I don't know why the book used capitals on this problem. That doesn't matter. I'll just make them all capitals. Okay, so fill it all in. So log of 300 divided by, what am I going to divide by in this case? Yep, 2.5 plus 4.3. Okay. So all that data, that would be measured somehow by some equipment. We'll plug that in and we'll see what the intensity is. Yep.
Are we assuming that this is log base 10?
Yes, because whenever you don't have a base written, the base is always a 10. Yep, this is base 10. So log of 300 divided by 2.5, and then plus 4.3. Okay, so that would be a magnitude 6.4 earthquake. They usually round the magnitude to one decimal place. Like when I've heard it on the news, I've never heard them say a magnitude 6.379181. They usually do 1. So about 6.4. And the thing about a logarithmic scale, which is what the earthquake scale is, when you go from like a magnitude 3 to 4, you might say, oh, it's a big deal. It's just, you just went up 1. Well, every time you go up one number, it's a factor of 10 times more powerful. So then if you go from like a 4 to a 5 magnitude, it's another 10. So if you compare like a magnitude 3 to a magnitude 5 earthquake, how many more times powerful is it? 100. So every number you go up on the Richter scale is a factor of 10. pH in chemistry works the same way. Any questions on that? All right, so we got through everything. So the plan for tomorrow is there'll be a review guide on Schoology, and we'll go over the homework, and then you'll have all class to work on that or ask me any questions. And that review guide covers exactly what's on the test. So that's your topics for the week. Okay, it'll be on that. Okay, so we did the top part. So it's page 301. Okay, 1, 5, 8 through 10, 16, 23, 25, 28, 42, 52. Okay, and as a reminder, I will be after school for extra help tomorrow. So I will be here tomorrow.